Hello everyone, I am Dr. Karthika from Department of Biomedical Engineering, SNS College of Technology, Coimbatore. In this October 2025 lecture series, we are going to talk about the ECG, cardiac electrophysiology, in biosignals and their characteristics in biomedical signal processing. First of all, we have to understand the heart's electrical symphony. First thing, here we have 5 action potential phases, and here we have resting potential, rapid depolarization, early repolarization, and final repolarization and plateau phase. Here, in this non-invasive recording, ECG captures the voltage differences on a skin surface, and which was formerly said by R. Willem Einthoven in 1902. Here, the main thing is we have to illustrate the waveform components. Here we have P wave, QRS complex, and T wave, which tells the cardiac activity story. C. In our design thinking stage 1, the first one is empathize, capturing tiny signals and emit noise. Here the signal challenges are normally ECG signals are more or less which is less than 0.5 millivolt amplitude and which is buried in plus or minus 300 millivolt offsets, and power line interface at 50 or 60 hertz, and muzzle artifacts and motion noise are considered here. These are all the main signal challenges. And next one is our clinical reality. Here the clinicians need crystal clear signals for accurate diagnosis, like electrode skin interface, variability, and environmental interface. It should be clearly stated in our device. And here our empathy insight is every missed beat, it could mean a missed diagnosis. C. In our defined stage, here we have to pinpoint our signal processing challenge. Here our challenges are noise cancellation, amplification precision, and feature preservation. Here, while removing power line interference, muzzle artifacts, and baseline wonder, without losing diagnostic information, which is our main thing in noise cancellation. And while coming into amplification precision, here we have to boost our microvolt cardiac signals to measurable levels while maintaining signal integrity as well as avoiding saturation or distortion. And our third one is feature preservation. Here we have to maintain critical diagnostic features like ST, QT intervals, and stable arrhythmia patterns during the signal processing. See, in our stage 3, our IDH stage, which involves instrumentation amplifiers, analog pre-processing, and integrated solutions. Here, in this instrumentation amplifiers, we have high input impedance and exceptional common mode rejection ratio, and we have to amplify differential cardiac signals while rejecting environmental noise. This is our main thing. And analog pre-processing, here we use bandpass filters and notch filters to remove baseline drift and power line interface before analog to digital conversion. Because our devices are digital devices, so we have to convert our analog signals into digital. And the integrated solutions, which involves modern microconverters, combine ADC, microcontroller, and digital signal processing in single chip solutions for portable ECG devices. See here in this prototype part we have multi-domain analysis, time domain, frequency domain, and time frequency. In this time domain part we have QRS detection, beat to beat intervals, and frequency domain we have spectral analysis for arrhythmias. Time frequency we have wavelet transforms for transient events. See, in our part deep learning for automated ECG analysis, here we have classification accuracy about 98% and arrhythmia reduction is 95% and continuous monitoring is about 24/7. See our real world impact from EP labs to wearables. Here are electrophysiology labs. Here are high fidelity signal acquisition, which enables precise cardiac mapping, which is converted into consumer wearables like smartwatches and portable ECG devices. And finally, we'll have a clinical decision support with the help of this consumer wearables and this EP labs, which provides real world impact from EP labs to wearables. This AI integration, which reduces clinicians' workload while improving diagnostic precision and patient outcomes. See here, I've included one activity for easy understanding. Here we have interactive simulation of heartbeats. Here we have activity, and the objective is how ECG reflects various heart conditions and how they change with different inputs. Here our conclusion part. Here our main thing is bridging engineering medicine and innovation convergence and global health impact. With the help of AI support, we can easily achieve the high precision and accuracy in our ECG monitoring activities. Here I've included two assessment questions taken from GE Healthcare. See here the two assessment questions and summary about mind map for ECG and cardiac electrophysiology, which starts with understanding cardiac signal and ends with a real world impact. And final, these are the references for the ECG cardiac activity in signal processing. I think we'll get a clear understanding about what is ECG and the activities behind ECG. Thank you for watching.